You see the drive is used the least because it's one that's controlling the actual power that goes into the motor. Supply and return fans are used. Cooling towers are using VFDs now. One of the issues with cooling towers is where do I put that VFD? Because they're not designed to be mounted outdoors. So you need a way of doing that, either a NEMA 3R case, or we'll put the drive inside a building that is, better temperature control. Drive is what, 0 to 122 degrees. So you're in a very tight range, and if you're in a place that's -10 or 120 degrees sometimes, it gets hot or cold, you would be in a tough spot leaving the drive exposed there. So you'd want some way of taking care of it. Boiler pumps and fans, of course. Kitchen hoods. I've seen them in all these applications. And you got pretty pictures. These are the a VAV system for a fan. And these are the VAV boxes, of course, you're all familiar with that. And in many cases, you have a bypass taper. But a VFD now controls that fan. You can have a lot better, tighter control, and you save more money by putting a VFD on the fan. And we'll get into where the cooling towers, same thing. You're controlling the motor. Wiring a single motor. PID application, there's a couple of ways you can do PID. Now you can hook a controller directly to the NXS or the smart drive. You can also do it in the core, but never knows how to do that. It's we haven't got that keypad set up, so it's simple to do it. It's a lot of code putting in there to make that work. But you can do it, controller, a sensor like a P7640, like this one, connected directly to the drive. It'll work that way. Since I sell controls, I prefer that you put a P775 on there and go through that with the sensor and then have that drive with a 420 output. The advantage of that, of course, is you're playing with this and your customer's not touching that. XL500 router, for those of you who've seen those. This is a DDC interface. Now you can connect it to a DDC system either directly through the analog output, and you can feed back into it through the analog inputs. There is a feedback capability on these drives. I don't know any drive that doesn't have that. You could also talk on a network to them. The smart drives come with BACnet and Modbus built in. You can add a LAN card if you do it LAN. And I've always asked, since we do so much with LAN, how come we don't have LAN cards built in? It's real simple. LAN charges for their chips, for BACnet doesn't. And so you'd have to pay the royalties if you built in every one, and this is a dog-eat-dog market. Drives are, there are 200 manufacturers out there, about 3,000 different brands. So it's, in order to keep the price down, we make the card separate rather than incorporate. But BACnet is in there and Modbus is in there. Now, when you're setting up a drive, a couple things you look for. First of all, you need to order the right horsepower and the right voltage. So you look at the motor, and for those of you who are experienced and have worked with motors before, you know that when you go to look at the motor plate, you bring a rag and some squirt cleaner, because chances are that motor plate is dirty. Hopefully no one painted over it. I've seen that. We'll paint everything blue today. Okay, well, it's going to be hard to read the plate, but if you can get the plate clean enough and you can read it, what you want to do is check the RPMs, the amp draw, the horsepower, volts, and also the insulation class of that, go back here, the insulation class here of the windings. Because a drive puts heat on that motor. the low frequency harmonics start heating that motor. And so you want insulation on the motor that'll handle that. Now, most of the newer motors are pretty well insulated. The older motors, you might have run into ones that didn't have a good class of insulation. But I think most, if not all the motors, insulation is not the issue. If you're going to put a drive on a motor, you want to make sure it's inverter rated. One that's designed to take a drive. There are motors out there that are not designed to take a drive. And some of you experienced that. I have. Now, I guess this is a good enough time as any to talk about that. There are two types of noise that a drive puts out. One is the high frequency harmonics. And we have a whole slide thing on harmonics we're going to get into. And the other one's low frequency harmonics. You know, you have a frequency, carrier frequency, let's say putting out 3,000 hertz. That means you have every half of that, a quarter and so on, there's a harmonic going out. So it's actually broadcasting. I don't know if you guys are old enough to remember, but in the old days, this is an AM station. That's where all talk radio is now, but AM station. And you, we tune it to like 1200, and all of a sudden you pick up the station that's on 600. Well, how am I doing that? Well, you're picking up a harmonic of that station on your radio. Radios are better, transmissions are better at filtering those things out today, but you still get harmonics. Well, you get the same thing on a drive. You got this frequency going out, and the harmonics come out, the high frequency and low frequency. Now, the high frequency harmonics are what screw up your radio. You know, I had one guy tell me, yeah, we put a new drive in someplace, and it wasn't a Honeywell. That's before we had it. He said, yeah, and the nun who was in charge said, I can't listen to my radio station anymore. She was with AM. I can't listen to the radio station anymore. All I get is buzzing noise. What's happening? He said, I don't know, man. Put it in a cheap drive, didn't have a filter. That's the high frequency. On the low frequency, it puts out noise that you pick up with a scope, and it puts it off the input. So that's why you see the line reactors on the inputs, because the low frequency harmonics are what kill the motor and also screw up your computers and stuff in the building. I had one job where they had a flame safeguard control, ARM 7800 controller, running a burner, and it kept blocking out. And of course they said, we got a bad control. They bring it down to wholesaler tested it. It's down to Cincinnati, and it works fine. It keeps blocking out. So they took a new one, put it on there, blocks out. And to find out there was harmonics on the line that was confusing the controller because the AC coming in wasn't pure. And so he had to put a filter on his controller. Not knowing where it came from, I can tell you where it came from. It came from some drive somewhere, or maybe a bunch of drives. That was the lowest cost ones. Or like the core. I mean, it's a lower cost drive, but it doesn't have the filters. So filters are important. Since you're putting harmonics to a motor, and low frequency harmonics happen, you have to make sure the motor is grounded and the drive is grounded. Also, the longer the distance of wire, you know, you can put 600 feet, but when you start doing 600 feet, you're going to get harmonics on there, and that's going to do a number on your motor. So you got to ground, you have to shield that, ground it every 20 feet or whatever, and that cable, if you're going to do that with long distances, do 10 or 15 feet, it's not a big deal. But in some cases, they require filters on the outputs to protect the motor. But if your motor is not designed for an inverter, for a drive, what happens is, for instance, the bearings are the latest thing now. The bearings in the old days were brass, steel, they conducted electricity beautifully. No problem. You worry about the insulation class. In the big motors, never a problem, because they have the brass or the steel or the copper bearings. It conducts current between ground and the arms. No problem. And you remember, your low frequency harmonics are creating current on that armature. Now, if the bearing happens to be a composite material, you know, epoxy and steel, epoxy and whatever, carbon,